Well, hello, everyone, and welcome to our first lecture on number theory. You know, number theory is one of the oldest branches of mathematics. It's been around for hundreds of years. There have been a number of interesting results that have been looked at over those hundreds of years, some of which are still not fully resolved. It's an ongoing field of research. It's a topic that is captivating for many people because many of the problems in number theory are actually very easy to state. These are results about whole numbers, right? That we all learn about as young children. You know, 1, 2, 3, 4, 5, 6, right? Whole numbers, those are integers. And there are some very deep results about integers. And there are some conjectures about integers that have been very hard for mathematicians to prove over the centuries. It's one of the things that I find fascinating about the subject, and it's one of the things I think attracts a lot of people to it. In this class, we're going to learn a lot of different things about number theory. We're going to see a lot of theoretical results. This is, after all, a branch of algebra that you could think of as belonging to the pure mathematics concentration. But I want to stress also that number theory is very applicable. It has practical value. And it's a subject that, even in today's modern times, is actually quite relevant, particularly in areas like computer science, as well as cryptography. And in fact, we're going to be studying how ancient results in number theory are still relevant today in the modern crypto systems that are used to protect your personal information on the internet, for example, that can sort of keep conversations and communications and sensitive information, keep that protected. We actually can use number theory, or at least the theoretical underpinnings of number theory, to help us understand how in today's modern age, we can protect our private information. So it's a deep subject. It's been thoroughly studied, and many easy to understand problems have led to some quite deep results and conjectures, and in some cases, challenges that mathematicians are still working on to this day. Number theory, of course, it relates to a lot of other branches of mathematics. And even though you would view it as a part of algebra, it has applications in other fields, such as computer science, such as complex analysis, and so on. Combinatorics is another area. So we're going to find that this is a quite central subject that has a lot of great value. And it's great that we're going to get a chance to spend this course learning about number theory and how it has developed and how it is still important to this day. It's been around for, as I said, centuries, right? It's one of the oldest branches of mathematics that you could ever imagine. And yet, even in today's modern times, new tools are being developed to try to address some of the current challenges with cryptography and with theoretical problems in number theory as well. So there will be a balance in this class between the applications and the computations, right? Things where you're solving equations using integers, where you're coding information using a crypto system. Those are practical computational aspects of number theory that we're certainly going to be looking at. At the same time, we're also going to look at a lot of the theoretical side of number theory. We're going to do a lot of proofs. We're going to learn about properties of integers and how they can be used to make more theoretical statements about the way the integers work and the way that number theory works. And with time permitting, I'm hoping to spend some time looking at some of these big theorems, these big conjectures, these open problems that have been around for a long time. Not that I'm expecting to solve them necessarily in this class, but I at least want you to be aware of some of these things and to be aware of some of the problems that people have really been focusing on. Now, in the context of our textbook, the first chapter is kind of a review. And there are a couple of things I want to mention. I'm going to go up to my board now. I'm going to write down a couple of things that I think would be good for us all to come into a class like this ready to go with. Okay. And the first one is, so I'll just call this things to review before we actually get into the number theory. The first thing that is quite relevant to number theory, guys, is the use of induction. When you're trying to prove that a statement is true, there's maybe some statement that is indexed by the integers or the positive integers or something like that. When you're trying to do those types of proofs, one of the most powerful and commonly used tools of proof is induction. So induction is a strategy of proof. So I will just say C, strategies of proof. And when I'm saying strategies of proof, I'm actually referring to a class. At Cal State Fullerton, we have, of course, a class called Math 280, and it is exactly this, strategies of proof. And it's intended to help students make that transition into a more theoretical class like this one. So strategies of proof, as I mentioned, this would be Math 280. For those of you who have been at CSUF for a while here at Cal State Fullerton, if that's a class you have not taken, I hope that you've taken something equivalent to that class somewhere at some point. If you have not done that, if you haven't had much exposure or experience with writing proofs and looking at different ways of proving things, please do come talk to me about that. I want to make sure that this is a class that you're going to be well suited to and well prepared for. So strategies of proof. And one of the main strategies, as I mentioned, is induction. You have basically with induction, you have some statement. And the statement might be, it's a proposition. So it's sometimes referred to as P of N, right? But this is going to be some statement that applies, for all N in the integers, for example. Or it could be the positive integers or the negative integers or some subset of the integers, right? But you have a statement like this that you want to prove. And generally what you do for induction is you assume that the statement is true, P of N is true, and you use that sort of stepping stone to show that the next version of the statement, the N+1 version, is still true. So this is kind of how induction generally works, and it is something that is particularly useful for number theory. And so we are going to need this strategy a lot. You know other strategies, probably proof by contradiction, direct proof, sometimes proofs by cases. We'll be using proof by cases in this class as well. So there are a number of strategies of proof that are going to get used in number theory. And I just want to make sure that everybody has had a chance to get well prepared with their honing of their proof strategies as they come into a class like this. Another thing that's mentioned at the beginning of our book, in the chapter 1 of our book, is the binomial theorem. And let me write it down here. This is a theorem that basically gives you a way of calculating, let's say, the nth power of an expression of the form x plus y. And the formula for this, I'll just go ahead and write it down here. You notice that we're using a lot of integers. N is generally an integer. K is going to be the index of this summation from 0 to n. And then we're going to have this so-called binomial coefficient here, n choose k. I'll write down in a moment what that is. And then it's going to be a combination of powers of x and y. Now, the x and the y actually don't need to be integers. They can be any kind of real numbers. But when I look at the terms of this expansion, right? The number of x's and y's that I have in each term is always going to add up to n. So you have some x's and you have some y's, and collectively they add up to n of those x's and y's together. But maybe we have k x's and n minus k y's. Those terms will occur a certain number of times, which this coefficient keeps track of, right? And that coefficient is, as I said, it's written as, well, it's pronounced n choose k. And in case anybody is rusty about this, just want to remind you that it can be written using factorials pretty easily. So if you need to, take a few minutes and look up the binomial theorem. It's something worth knowing anyway, even independent of number theory. But this is just a kind of a combinatorics expression. If you've taken combinatorics, you may have seen this on a pretty regular basis as well. But it does show up here in the binomial theorem. Okay, so a couple of things to review from the first chapter of our textbook: induction and the binomial theorem. Now, the first chapter of our book also has a good bit of history. One of the things I like about Brualdi's elementary number theory book is that it does have a lot of historical information. We can learn about sort of the events that transpired that developed number theory into what it is today, and many of the players that were involved in moving the field forward. So if you're interested, of course, at any time, reading that history in the book is a great thing. It's not necessarily the stuff you'll get tested on regularly, but I find it fascinating, and I think it's very interesting to get that extra background, if nothing else, just to kind of inspire you a little bit with this subject. Just as a little bit of a notational preparation, this is also something that you would want to know right from the very beginning. Some of the notations that you're going to see me using throughout this course on number theory. Of course, you've seen me already use this sort of math boldface Z, right? So this is the set of integers. And this is referring to all integers. Sometimes we only want to take the non-negative integers. And so these are sometimes called natural numbers, and I use an n for this. This would start with 0, and then 1, and then 2, and then 3, and so on. So you're taking all of the integers that are at least 0. Okay, so that is the natural numbers. I should warn you that some people will not include 0 as a natural number. It kind of depends on who you're talking to. I would say it's not universally accepted. I will not use the n notation very often because of that confusion. I will generally just write out what I mean. Okay. Now, something that's maybe a little bit less confusing that I will sometimes use, if I just want the positive integers, I might just write it this way: a z with a plus on the end of it. So this is referring to all of the integers 1, 2, 3, 4, and so on that are strictly greater than 0. And of course, I could do the same thing with the negative integers. I could put a minus and look at the negative numbers, -1, -2, -3, and so on as well. So we certainly can look at subsets of the integers. And these are just some ordinary notations that you'll see me using from time to time. So if you look at the first chapter of our book, you'll get some of this background, some of the things that I've kind of highlighted here on the board. But where the real meat of the number theory begins is actually in chapter 2 of our book. And that's where I'm going to actually sort of begin the focus of my notes and my lecture that we're starting with today. As always, guys, I would want to encourage you to pause the video if you need to stop and reflect on anything, or if you're just behind on writing down notes. It's good to understand what's going on and not just be writing it down frantically. So one of the powerful advantages of a video is that you can stop it and you can pause and let things come at the pace that you're comfortable with. But without further ado, I'm going to clear off most of my board right now so that I can actually start talking about chapter 2 of our book, which is about the subject of divisibility. So let me go ahead, I'll clear this space off, and we'll get into it. I'm excited. I hope that you're excited because this is one of my favorite subjects. I've really enjoyed teaching this class a number of times, and we're going to have a lot of fun with it. I'm pretty sure. So chapter 2, as I mentioned, this is all about divisibility. And I will start off, usually with a new chapter, there's going to be a bunch of definitions just to kind of get the ball rolling. And that is exactly the case here as well. So I'm going to write down the definition of what it means for one integer to divide another and so on. And this is in our book as definition 2.1. So I'm going to go ahead and start with this definition. What we're going to do is we're going to start by considering an integer b. So b is an element of the integers here. And we say that b is divisible by some other number a. Now I want to emphasize here that a is not 0. So b is divisible by a. And this is usually written, and we have to get this right, which number goes on the left of this bar and which one goes on the right of this bar. The number on the left is the one that is doing the dividing, and it is being divided into b. Okay, so a is dividing b. In other words, b is divisible by a. And this is if there exists some integer c. There exists an integer c with b equal to a times c. So this is kind of the key equation. And I just want to make sure everybody's clear that the a goes on the left of the notation because a is dividing b. In fact, so we say that a divides b in this situation. A divides b. We can also say it a different way. We can say that b is a multiple of a. That's another way to say the same thing. And we call a factor or divisor of b. Okay, so there's a lot up here. This is kind of a long 3-4 lines of writing down a definition, but it's all kind of wrapped up in this single idea that one number is dividing another if you can find some integer c such that the second number is just a times c. All right. I should mention here that a is also an integer. If we go back at the start of this definition, I want to just add that right now so that there's no confusion later. So both a and b are integers. We're only playing with whole numbers right now. So you take two integers a and b. A divides b if there exists a c such that b is equal to a times c. And I can also mention that if b is not divisible by a, then we actually can write that with a notation as well. And you'll see me doing this a lot, so it's good to include this. We can use the same notation, but just put a slash through the divisibility bar, that vertical bar that's representing a dividing b. So it's pretty easy to write down some examples of this. Again, we're just playing with whole numbers. So for example, -4 divides 12, right? Because I can find an integer c such that 12 is -4 times c. Namely, we just choose c to be, in this case, we would just choose c to be -3, right? So -3 times -4 is equal to 12. So that's one example. Maybe let's write down a few more examples here. I will note that 10 does not divide 12. You cannot multiply 10 by an integer and get 12. Another one that's worth noting is that every number divides 0. So if b is 0, notice I said that a is not 0, but b could be 0. And if b is 0, then we can always just choose c to be 0 to satisfy this equation. So in fact, not only does 6 divide 0, we can actually just say that a divides 0 for all a not equal to 0, right? And again, we would just simply choose c to be 0 in our definition to justify that. Okay. These are pretty basic properties. I just like to write them down so we have them for the record here. I should also mention that for all integers b, 1 always divides b, right? And b also divides b. So every number, every integer has at least 2 divisors, right? Namely 1 and itself. Those are always divisors. Now, if b is 0, of course, then we don't want to use itself as a divisor. But for any other integer, there is always these 2 divisors that are guaranteed. Okay, so 1 and b. Do another example here. What are the divisors of the number 1? So if a divides 1, then we're saying that 1 can be expressed as a multiple of a. Well, there's not very many choices for a that would make that work. It turns out that a would have to be either plus or minus 1. Okay. Notice I'm not writing down formal proofs of all of this. It's because it's almost just automatically from the definition, right? If you just think about the definition for a minute, none of these things are terribly deep. Number 6 is slightly more abstract. This one you could think about writing a proof for. So if a divides b and c divides d, then AC divides BD, right? Maybe just for the record, I will write a proof of this just so we can kind of practice how to write a proof of something in number theory here. So what we could say here is that from the assumptions, now, of course, the definition of divisibility involves the existence of C, but I'm already using C in my statement here, so I'm going to use some different letters. I'm going to actually use the existence of 2 integers x and y, I think, with what we can say is that b is equal to ax and d is equal to cy. So we can do this. And the whole point now is to somehow write BD as a multiple of AC. And that's very, very straightforward, right? BD is actually just AXCY, if we want to think of it that way. And this just becomes AC, put those together, times XY. All right, and so we can conclude that AC divides BD now. And I'm just going to add a little comment here at the bottom. XY is actually still an integer. technically, whatever this multiplier is here has to be an integer. So just to really clarify that, x times y is a product of two integers, and so it's an integer again. Okay, so we have that. Let's see, I might have another one or two more of these kind of basic facts to jot down. Yeah, number 7 up here. Number 7, can you guys see that? Yeah, okay. So number 7 up here is just that if two numbers divide each other in both directions, so if A divides B and B divides A, right? Then that actually would mean that A is plus or minus of B, right? They are actually either equal to each other or negatives of each other. Okay. And again, this is not hard to prove, but let me just do it. Now that we're getting into some slightly more generic statements, they can actually be proven a little bit more on a rigorous level. So, so for example, for the proof, and it's an if and only if statement. So of course I have to prove it both directions, right? I have to prove it both directions. If I want to focus on the backwards direction first, right, then I'm going to assume that A is equal to plus or minus of B. And that actually leads me to two cases. So just to be really thorough here, I know for some of you this may just seem like an obvious statement, but I just want to show you how writing down the proof might look, right? If we want to try and be pretty rigorous about it. So we have two possibilities here. One would be that A is equal to B, right? And then I'll leave a little room to write that one out. And then the second case here would be A is equal to minus B. So we have two cases like this. And what we can say, if A is equal to B, then that tells me that B is equal to A times 1. And A is equal to B times 1. So the integer C in the definition of divisibility is just 1 in both cases. So what we're saying here is that A divides B and B divides A, which is what we wanted to prove in this backwards direction. Again, just a reminder, feel free to pause the video if I'm talking too fast or you need a little time to write this down and kind of get it clear in your mind. There's a little bit of a glare on my board. I hope this is readable. This just says A equals B times 1. This just says B divides A. The second case, of course, is almost the same thing. In this case, we can write B as A times negative 1. And we can also write A as B times negative 1. And so again, A divides B and B divides A. We prove in both directions that the first number divides the second. All right, and then the forward direction of this proof, I have to prove the other way, right? So in this case, I would be assuming that A divides B and that B divides A, right? I want to prove from left to right, from this side to this side, I got to start with the assumption on the left. By definition, right? What do these divisibility statements mean? Well, it means that there exists, I'm going to use the integers C and D here. So C and D, which are integers, such that B is equal to A times C and A is equal to B times D. This is kind of the definition. Well, this actually tells me if I kind of put these two things together, a little box around both of these two equations here. If I put those together, I can actually take the first equation, which is B, it's equal to A times C, but I can go ahead and put in what A was. So A is just BD. So we end up with this equation right here. And of course, this tells me now that if I cancel the B, by the way, A and B are both non-zero, because you can't even talk about A dividing B and B dividing A unless they're both non-zero. So we'll take that as the first assumption, okay? So now we've said that C times D is equal to 1 in this case. And my goal is hopefully ultimately, to prove that A is equal to plus or minus B. But you see, if C times D is equal to 1, this implies that C and D are either both 1 or they are both minus 1, right? They're going to be the same, and they're both plus 1 or they're both minus 1. And if I now just think about what that tells me about these two boxed equations, we can see that this implies immediately that A is equal to plus or minus B in that case. Hopefully that makes reasonably good sense. So it's a nice little proof. If two numbers are both dividing each other, then they either have to be the same number to begin with or the negatives of one another to begin with. All right, let's do one more sort of generic result here, and then I think we'll move on. This is just basic playing with the definition. I just kind of want to start with that and go from there. Okay, so one more result here. I guess this is going to be number 8, which just says that if A, this is actually a pretty important one, if A divides B and A divides C, then A will actually divide any integer combination of B and C. So it would actually divide BX plus CY for all integers X and Y. So no matter what X and Y are as integers, A will divide that integer combination of B and C. Again, this is very straightforward. I will write it down just for thoroughness here, just to be really complete. So since A divides B and A divides C, there exist integers. I'm going to use some different letters for this. I'll call them R and S, such that B is equal to AR and C is equal to AS. All right, and so then if I look at this new number, BX plus CY, this is what I would like to show is a multiple of A. Well, I can just plug in what B is. B is AR, so that gets multiplied by X. C is just AS, and that gets multiplied by Y. And now I can factor out the A, and I just have RX plus SY. And that shows that A divides BX plus CY. And I'll just mention, again, this is pretty obvious. You don't really have to write this down, but I will just for total thoroughness, that the multiplier of the A is legitimately an integer. After all, X is an integer, Y is an integer, R is an integer, and S is an integer. So this is just a combination of integers being added and multiplied together. And that means it's still an integer. Okay, fantastic. All right, so we got quite a bit of practice here already on the definition of divisibility. I'm going to go on to another definition. Again, very, very basic stuff that may be fairly familiar to many of you, but I still believe in sort of taking things carefully from the top. So I'm going to state this definition kind of from scratch here, definition 2.2. And what it says is we're going to take two integers A and B, And I'm just going to mention here that they should be not both 0. We take two integers that are not both 0. I want to define the greatest common divisor. You've probably heard of this before, right? The greatest common divisor of A and B. And this is usually written GCD of A and B, or sometimes, I think this is not the best notation, but sometimes people will just write A and B in parentheses like that. I prefer to add the words or the letters GCD in front of that, just so it's really clear. And what is this greatest common divisor? Well, it is the integer D, and it needs to be a positive integer. So I'm going to use my Z plus notation here. It is the D in the positive integers with two conditions. First of all, D has to divide, has to be a divisor, a common divisor of both A and B. So D divides A and D divides B. And secondly, if there is another number C that also divides A and B, then that number C should be less than or equal to D. So D is the greatest, the biggest, the largest of the common divisors. So the first part of the statement just says that D is a common divisor of A and B. And then the second part of the statement says that if there was another common divisor of A and B, D is the larger one. So this is the idea of the greatest common divisor. Now, just to write down a couple of examples of this, I'm sure you probably looked at this in the past, but it doesn't hurt to kind of get ourselves a little bit of practice here. Let's say I wanted to know the greatest common divisor of -20 and 28. Feel free to pause the video if you want to think about these exercises yourself before I just give you the answer directly. I don't want to steal your fun from you, so feel free to go slow and pause the video and try to answer this yourself. We're looking for the greatest common divisor of -20 and 28. I should mention the minus sign really doesn't matter here. Ultimately, even though the A and the B could be negative, the D in the definition will have to be a positive number. And if we just were to look at a positive 20 and 28, we could come up with this answer. So we're looking for a common divisor of both of these numbers. So obviously 1 divides everything, right? So 1 is a common divisor. The question is it the greatest common divisor? And you think probably not, because both of these numbers are even, which means that 2 should also be a common divisor. And in fact, if you think about it, we can get even a little bit larger than that, because it turns out that 4 divides both of those numbers as well, right? It divides -20 and it divides 28. Turns out that is the largest one. Okay, that is the largest one. Just to really emphasize this thing about negatives, even if I took something that was fairly obvious, like, I take -6 and -6, it seems like, well, obviously -6 divides both of those because every number divides itself. But again, we have to make the greatest common divisor positive. So this would actually end up being equal to +6, okay? Another one that's kind of just a weird, funky case is, what if you have 0 in your list? So let's just say you had 0 and B. Now, in this case, so this is actually, let's just use A. I'm sorry. A is a little bit easier to not get confused with a number. The thing here is, remember, A and B are not both 0. So in this case, I'm assuming that the A is not 0. And so we're looking for divisors, common divisors of both of these. Now remember that every integer divides 0. So we're really just looking for the largest integer that divides A. And the answer would just be A itself, right? A itself. However, if A was negative, we would again need to make it positive. So I claim the answer is absolute value of A. This is for all integers A that are not 0. Okay, so pretty easy result right there. For examples of this definition. Now, we'll be learning an algorithm very shortly for how to find the greatest common divisor of two integers. So even if these were fairly obvious, you could imagine with some bigger numbers, it might not be so quick to know what the greatest common divisor of two numbers is. So there is actually an algorithm for it. It's something called the Euclidean algorithm, and that can be used to determine the greatest common divisor of two numbers. I'll be reviewing that with you in the very near future. But right now, just kind of want to play with the definition though, okay? There is a result about the greatest common divisor that a lot of people aren't really aware of, but which is actually really useful. And so I would like to put this on the board. This is actually more important than it maybe at first seems, but it is worth really getting this down. So it is a theorem from our book. It's theorem 2.3. And what this says is, given A and B in the integers, and again, we're going to say not both 0, just to kind of set up the same assumptions as when we're talking about the greatest common divisor. So given those two integers that are not both 0, there exists integers x and y, so x and y in the integers, right? Such that, so here's the important thing. The greatest common divisor of A and B, right? If we look at that, we can actually write it as an integer combination of A and B itself. So this is kind of cool that you can actually write the GCD of A and B as an integer combination of A and B. Now the x and the y here, they don't have to be positive. You can have negative numbers for that. It's anything goes. And it turns out, maybe before I go any further in talking about the theorem, I'll just make a remark here that the x and the y are not unique. Of course, a good thing to be able to do is think about giving an example to show that for a given choice of A and B to start with, starting with these two numbers, actually possible to find more than one way to write the greatest common divisor of A and B as a combination of A and B. So I'm going to do that. I should give an example here. Let's just suppose, I'm going to make it really easy, by the way. I'm just going to take A to be 3 and B to be 2. And these are obviously extremely small numbers. The greatest common divisor of 3 and 2 is pretty clearly going to just be 1. Right, so we have that. And what I want to do is I want to write 1 as an integer combination of 3 and 2. And you can see, for example, that one way to do it would be to write this as 3 times 1 plus 2 times minus 1. So I could choose x and y to be 1 and minus 1. That's certainly one way to get away with doing this. But there are other ways to do it. We could also write this as 3 times minus 1 plus 2 times 2, right? And that also is equal to 1. And so the x and y choice is not unique. How do I show you that? Well, I give you two different choices of x and y that will accomplish the job of satisfying the box up here. That's kind of the idea. Okay, So this theorem is really useful in that it allows us to write the greatest common divisor of two numbers as an integer combination of those two numbers. Not a unique choice. And in fact, the theorem doesn't actually tell you how to figure out x and y. It turns out that that Euclidean algorithm that I was talking about a few minutes ago, actually not only will it find the greatest common divisor of a and b, it'll give you one of these integer combination expressions. So that's kind of handy, and we'll see that very shortly. Of course, in a class like this, we would want to give a proof of this theorem. I want to point out that the proof of this theorem relies on another result, which is actually also quite important, called the division algorithm. So let me come over on the left side, and I'm going to write down the division algorithm. This is also in our book. It relies on the division algorithm, and this is actually in section 2.2 of our book. I don't know that this has a number associated with it in the book, but let me just state this here. This is, as I said, it's in section 2.2. It says that if a and b are integers with b greater than 0, then there exist unique integers q and r, so q and r in the integers, with a equal to q times b plus r. That's actually the most important part of it, right? And there is another important part of it, though, which is that the r has to be somewhere less than b. It has to be at least 0, but it has to be less than b. So this is the division algorithm. By the way, I should mention, guys, that in the statement of the division algorithm here, the q and the r stands for the quotient and the remainder. So what you're really doing here is you're taking your two integers a and b, and you're going to divide a by b. Whenever you do that, of course, there will be a quotient. That's what q is. So you took a, you divided it by b, you got a quotient q, and then some leftover remainder. I know this is a little hard to read, but this just says that the remainder should be less than b, right? And in so doing, you actually end up with a unique choice of the q and the r. So the quotient and the remainder are unique as long as you force the remainder to be between 0 and b minus 1. Okay, so the first thing I would like to do is prove the division algorithm. This is a tool that we will need that will allow us to then come back and prove this really important theorem about the greatest common divisor on the other side of my board. So for the proof here, I'll start my proof right here. What I'm going to do is I'm going to consider all of the positive multiples of b, and I'm going to make a set out of those. Okay, so I'm going to look at b, 2b, 3b, and so on like this. All of the positive multiples of this integer b. Okay, now of course b could be, it's greater than 0, so it could be that you have a positive number and then you're just multiplying it by these positive multiples. This is a collection of positive integers, is what we're trying to take a note of here. Okay, so then what we're going to do is we're going to actually construct q right now. This is the q for the theorem, the quotient. Q, we're going to let that be the largest integer. This is going to be the largest integer with Q times B less than or equal to A. So we kind of look at all of these integer multiples of B here, and we find the largest one that is still less than or equal to A. All right. So this is going to be the basic idea. So in other words, what we're saying is that if we go to the next multiple of B, right, that this is strictly greater than A. All right. So this is the setup that we want to have right now. So far, hopefully that makes sense. So we set things up this way. Great. So what I'm going to do then is I'm going to look at this number that I'm going to define as R, right? And I'm going to define R to literally be A minus Q times B. All right. I'm going to define R that way. It's going to be A minus Q times B. Now, A minus Q times B is at least 0. We see that already. Okay, so we know that. And we also know that if we, I'll make this as a note right here. We also note that R is less than B. And why is that? R is less than B, and that is because, you know, A is less than Q plus 1 times B, which is Q times B plus B, right? So if I actually sort of take, if I take this inequality here, A is less than QB plus B, right? That's basically what this says. Right? If you take this inequality here, it just says that A is less than QB plus B. So R has to be less than B. See, let me just make sure that I'm being clear about this. So see, this implies, right? This implies that A minus QB is less than B. Right. And this, of course, is by definition, this is what R was. Okay, so we actually have been able to find an integer Q and an integer R, right? Such that, well, just from this definition, we basically have created this equation here for A, right? If you rearrange this box, you literally get this expression for A right here. So there's nothing that tricky about it. I do want to address, though, that we have to have the uniqueness part. The Q and the R are supposed to be unique. So let me write something about that right here. The uniqueness of Q and R. We've now shown that we can define Q and R in the manner that the division algorithm states. But another question to ask is going to be, why are they unique? Well, the way that uniqueness is generally shown is to imagine that maybe there was 2 ways to come up with Q and R. And so let's actually suppose that. Let's suppose that we can write A as Q times B plus R, but we can also write it as Q prime times B plus r prime. Let's suppose we can do that. And this would be where, right, where we know that 0 is less than or equal to both r and r prime, which are both less than b. Okay, so I'm making that assumption here that there may be two ways to do this. Well, what I can do then, guys, is I can take this equality right here and I can actually manipulate it a little bit. Namely, I can actually take the q minus q prime times b. I'm going to group those parts of what I've underlined here, right? I'm going to subtract the q prime b to the left side and then factor the b out of it. And then on the right side, I will have r prime minus r. So I'm just rearranging the underlined part when I write that down. But I want to point out that r and r prime are both between 0 and b, right? See that? R and r prime are both between 0 and b. So when I subtract those two numbers, it's got to be less than b for sure, right? It can't be more than that. And yet this expression is somehow a multiple of b. It is somehow a multiple of b. And that actually means that this multiple is going to need to be 0 times b. In fact, I want to point out also that this is going to be greater than negative b. So I'm sorry, give yourself a little extra room on the left here. You see, the r prime minus r, that difference, it could actually be negative because I don't know which of the two remainders is larger. Could be negative when I subtract them. However, because the r and the r prime are between 0 and b, when I subtract them, it's got to give me something larger than negative b, but less than b. So this actually implies now that q minus q prime is 0. In other words, q is equal to q prime. That much we have for sure. And if q is equal to q prime, right, go back to this underlined part that you see right here. If q and q prime are the same, then I actually could cancel. I could actually cancel those and therefore deduce that we also have that r is equal to r prime. So the q and the q prime have to match, and the r prime also have to match. And that proves uniqueness of our quotient and our remainder in this division algorithm over here. Okay. So I hope that all of that does make some sense. Okay. Great. So we're going to use this division algorithm to now go back and prove theorem 2.3. I'm going to erase on my board now. So if you need to pause to reflect on anything you see here or catch up on any notes, this would be a good time to pause the video because I'm going to give myself some more room now to write some things down. Okay, so get rid of this proof, first of all. And we've proven the uniqueness as well, so I'll take that out of the way. And let's talk about the proof of theorem 2.3. So proof of theorem 2.3, I'm going to try to put that one right over here. Okay, so here's what we're going to do. We're going to kind of start off with something that looks similar to the proof of the division algorithm. I'm going to make a set. I'm going to make a set that has all positive, I'm going to write this in words if you don't mind, the set of all positive integer combinations, the set of all positive integer combinations of A and B. So I'm gonna make that as a set. So I have A and B that are given. They're not both 0. And I'm going to take all positive integer combinations. In other words, let's write this out a little bit more mathematically. It's just some multiple, let's say U times A, plus another multiple V times B. These are what the integer combinations of A and B look like. And this is going to be such that, my little colon here means such that U and V need to be integers, because it says positive integer combinations. And the other requirement is that when we actually calculate U times A plus V times B, it's supposed to be a positive result. So UA plus VB is greater than 0. Okay. Now, if V is equal to 0, I just want to make an observation here for a moment. If V is equal to 0, if we consider that possibility, then of course, all I'm getting are multiples of A here. U times A is certainly there. And in particular, by choosing U to be either +1 or -1, right, I will be able to say that the absolute value of A is achievable in S. Right, so A might be negative, but I can use a -1 for U and create the absolute value of A. This is a positive expression, right? This is a positive expression that would belong to S, right? By taking U to be plus or minus 1, whichever one it is that makes that positive. Now, the only exception to that would be if A is actually equal to 0. Okay, so on the other hand, so this is unless A equals 0. So if A is equal to 0, then the absolute value of A is not in S, because S is supposed to consist only of positive expressions here. Okay, so if A is 0, then B is not 0, and we get absolute value of B in S similarly. So we can either A or B is not 0, because they're not both 0. And so we're going to be able to either get the absolute value of A or the absolute value of B in S. My main point is, the main point of all of that is kind of a long way of saying basically that S is not empty. S has something in it. There is at least one positive integer combination of A and B that ends up in this set S. Either A or B is not 0, and the absolute value of A and the absolute value of B would then be in the set S. So we have a non-empty set S here. And so then I'm going to let D be the smallest element of S. So what do we have here? We have a non-empty set of positive integers. So we're just going to take a look at that non-empty set of positive integers and grab the smallest one, and I'm going to give it a name, which is D. I'm going to call this one D. And since D belongs to S, it is a positive integer combination of A and B. So I'm going to write D as, well, let's just say AX plus BY for some X and Y in the integers. It turns out that the X and the Y, whatever they are that we're looking at right now, they are the X and the Y that we've been looking for in this theorem. And what remains to be shown, the claim that we are going to now hopefully justify, is that that D really is the greatest common divisor of A and B. That is our claim, that the D the smallest element of S is actually the greatest common divisor of A and B. Okay, so let me come back over here and try and justify this claim a little bit. So for the proof of the claim, actually, I'll start on this side, I think. So I'm just going to justify this claim. I'm going to go ahead and use the division algorithm right away. So I'm going to write A as Q times D plus R. So I'm going to actually divide A by D and get a quotient and a remainder, right? So there is a slight difference in letters here. I used a B originally in the division algorithm, but right now my D, notice that D is positive, right? So it can play the role of B from the division algorithm. And I know that I can find a unique choice of Q and R where R is at least 0, but less than D. Okay, so this is, of course, being done by the division algorithm. So we're applying the division algorithm to A and D, right? To A and D. This is what we're going to have. Now, of course, we can write R as Q times D. I'm sorry, A minus Q times D. We're going to write R as A minus Q times D. And that can be written, let's just move over here, write down a little bit more. This is A minus Q times, I'm going to put in what D was, which is AX plus BY. And I can actually now express this as 1 minus QX times A plus negative QY times B. So R is actually expressible this way. And what that is actually is this is an integer combination of A and B. And it's what R equals. R is an integer combination of A and B. Now notice that R is at least 0 and less than D. If it's less than D, right? If it's less than D, then it shouldn't be a positive integer combination of A and B. Why not? Because D was supposedly the smallest element of S, right? So what I want to say here is that since R is less than D, R is not in S, right? D was the smallest. D was the smallest element of S. So R is not supposed to be in S. And yet R does look like it's an integer combination of A and B. The conclusion is the only way that R would not be in S if it was an integer combination of A and B is if it's not positive. And the only way that R could be not positive, you look at your choices for R right here, right? It's at least 0, otherwise it's positive, right? So it has to actually be 0. R has to actually be 0. And that means, now I'm going to clear off this part, because we're kind of done with this part. If R is equal to 0, then we can come back and look at this division algorithm again. And we can say that thus A is equal to Q times D. There is no remainder there. The remainder, well, it was 0. It was 0. And so thus we actually know that D does divide A. And similarly, we're not going to write out the whole proof. We don't need to do that. But similarly, we can conclude that D divides B. And this means that D is a common divisor of A and B. D is a common divisor of A and B. Remember, if we're trying to claim that D is the greatest common divisor of A and B, so I first have to show that D is a common divisor of A and B. And then I have to show that there's no other larger common divisor of A and B, right? It's two parts. If you go back to the definition of greatest common divisor, you show first that D is a common divisor, and then that there's no other divisor that could be larger. So in fact, what we want to say next is, now we're still proving the claim. I'm not done with the claim yet. I've got that D is a common divisor of A and B, but I need it to be the greatest one. So suppose that there was another one. Let's just suppose, I'm going to use a C, I think, that there was another divisor C greater than 0 with C dividing A and C dividing B. All right. Well, then we actually know that C divides any combination. Remember, we had this, I think it was fact number 8 in my original examples of divisibility. But if C divides A and B, then it divides any integer combination of A and B, including AX plus BY, which just happens to be what D is, right? So C actually divides D, which implies that C is certainly less than or equal to D. And that proves that not only did we show that D is a common divisor of A and B, we've now shown that if there was another common divisor of A and B, I know this is a little hard to read right here. This just says C divides A and C divides B. If C is a common divisor of A and B, then it actually divides D itself. It's actually going to be a divisor of D, which means it's less than or equal to D. That proves our claim. This proves our claim now. And if we've proven the claim, then we're pretty much good to go, right? For this theorem, the greatest common divisor of A and B, we've now shown that it equals D, and D is AX plus BY. So there you go. This is the proof of theorem 2.3. Fantastic. There's a nice corollary of this theorem that I want to write down now that it goes hand in hand with theorem 2.3. So this is as good a time as any for me to state this. So this is just going to be a corollary of theorem 2.3. Let me just state this right here. Again, given the same assumptions here, A and B are integers. And again, I'm going to say not both 0. Then, if we form the set T, which is going to be the set of all expressions that are integer combinations of A and B, so AX plus BY, where X and Y are integers, if we look at that set, okay, so we know, for example, that the greatest common divisor of A and B is in this set by the theorem. Theorem 2.3 tells us that the GCD of A and B is, in fact, an expression that would be inside of T. But what the theorem is saying is that this set consists of all multiples of D, which is the GCD of A and B. So it consists, let me be very clear, it consists precisely of all multiples of the greatest common divisor of A and B. In other words, another way of writing that would just be simply that T is equal to the set of all integer multiples of the GCD. So where n is any integer, the set T is all multiples of D, all integer multiples of D. So I'm going to prove this as well. This is a nice corollary that we should also appreciate. I'm proving that two sets are the same. The set of all integer multiples of A and B, that set, T, is the same as the set of all of the integer multiples of D itself. Right, so this is what we actually would like to justify. Whenever you're proving that two sets are the same, you ought to be thinking about proving that each one is a subset of the other, right? And that's exactly what I'm going to do. I'm going to prove subset. In fact, I'm going to use this little symbol here, notation of a subset symbol. For the first part of the proof, I'm going to pick an element out of the set on the right and prove that it lives in T. And then I'll prove the other way around as well. So let's assume that n is an integer. And by theorem 2.3, I'm going to write the greatest common divisor of A and B as AX plus BY for some integers X and Y. So that's what theorem 2.3 allows me to do. I can write my GCD. That is what D is, by the way. D is the greatest common divisor of A and B. So I'm going to write it by theorem 2.3 as an integer combination of A and B itself. Well, then when I look at this number n times D, that's just simply n times AX plus BY. And that is, yet again, that is just simply A times NX plus B times NY. And that is what capital T consists of, right? Capital T just consists of any integer combinations of A and B. And I've got that expression right here. So anything that's a multiple of D is an integer combination of A and B. That proves that the subset from the right side is a subset of the left side. That's half the proof, basically. Although that's really pretty much the easy half. Okay. So what about going the other way around? What if we pick something in T? Well, consider AX plus BY, which is an element of T. This is just for some X and Y in the integers. We start with something that is in T to begin with. And we would like to show that it is a multiple of D. Well, the thing is, we know that D divides A and D divides B. After all, D is the greatest common divisor of A and B. So D, therefore, has to divide any integer combination of A and B. That was an earlier observation that we made. So D has to divide this guy. Well, that just means that AX plus BY is a multiple of D. Say AX plus BY is n times D for some integer n. And that proves that this element, ax plus by that we started with from T, does in fact live over here. It's a multiple of D. That's what this says. So we're actually done with the proof here as well. So that corollary is relatively straightforward to prove. And it just means that if you take all possible integer combinations of A and B, what you'll end up with is precisely all multiples of D. It's exactly all multiples of D. Okay. Well, a very special case that can sometimes occur with two integers, not both zero, is that the greatest common divisor could be equal to 1. And when that happens, of course, you look over here, the set T would actually be all integers, right? If you take all possible multiples of 1, you'll get the entire set of integers. Every integer can be written somehow as an integer combination of the A and the B that you started with. So this turns out to be a pretty important case in number theory, and it's worth writing a special definition for. Basically, when two numbers have a GCD of 1, we're going to call them relatively prime. So let me come back up and put that in the notes for us. So definition over here, this is a definition for us. Okay. Two integers, A and B, as always, not both 0, are relatively prime they are relatively prime if the GCD of A and B is equal to 1. GCD of A and B is equal to 1. I hope that's readable here. Okay, that means relatively prime. The two integers are relatively prime. So an immediate theorem that follows pretty easily from what we've already done, guys, Theorem 2.4, just says, well, as always, given A and B in the integers, not both 0, right? Then what we can say here, guys, is A and B are relatively prime A and B are relatively prime if and only if, remember that just means that the GCD is equal to 1. This is going to be if and only if there exist X and Y in the integers with AX plus BY equal to 1. No surprise at all, right? There's no surprise to this at all. If you need to pause and catch up on anything, feel free to do that. Or if you want to think about why is this true, just take a look at what's on the board and it's pretty much already spelled out for us. Okay. I am going to write down the proof just for the record so we have it in the notes, but this is almost should be thought of more like it's a corollary of what we've done before, right? It's not really anything particularly new. But I am going to still write it down as a proof. So for the forward direction of this, if I assume that A and B are relatively prime, that just means that their GCD is equal to 1, then we already have the theorem over here, guys, that says that 1 would have to be equal to AX plus BY for some X and Y, right? So in other words, this is just literally a special case of Theorem 2.3 that's already on my board. Okay. The backwards direction, on the other hand, also not going to be anything too crazy, right? So suppose this time I'll write out what I actually have for an assumption, that there exists integers x and y with ax plus by equal to 1. Suppose that we have that. Well, that just tells me that basically that 1 is in T. Okay? What is T over here? It's a set of all integer combinations of A and B. So in this case, 1 is one of those, right? So what we're going to say is by the corollary, 1 is an element of the set capital T that I'm referencing over to the corollary right now. 1 is certainly an element of T. So 1 has the form n times d. It's a multiple of d, right? For some n. For some integer n, right? So if 1 belongs to T, then 1 has this form, right? And that actually tells you that d has to be equal to 1, right? The d has to be equal to 1 because otherwise n would be a fraction to make this equation work. D does have to be positive, right? The greatest common divisor is always positive, so it can't be -1. If you're thinking, well, could this be -1 times -1? No, D has to be greater than 0. So it actually has to be equal to 1. And if the greatest common divisor of A and B is equal to 1, that means that A and B are relatively prime. All right, so that's pretty straightforward as well. So if two numbers are relatively prime, then it's possible to write a linear combination, an integer combination of them, that actually is equal to 1 in that case. And so that's one way to think about two numbers that are relatively prime. And again, this Euclidean algorithm that I'm going to talk about later will actually help us figure out a choice of x and y that will work. The x and the y are not unique right here. It's not a unique choice, but they do exist. They do exist. Okay. A couple of corollaries of this theorem that I'd like to record for the record here. Go ahead and I'm going to put one of my corollaries right here. Corollary 1. Okay, so this is the first corollary of theorem 2.4, which just says that if the greatest common divisor of A and B, if we call that D, okay, then the greatest common divisor of A over D and B over D will be equal to 1. So as soon as you have a greatest common divisor of A and B, you can divide A and B by that common divisor, and the two new integers that you have are now relatively prime. Right. So let's write down a quick proof of this. This is, again, not something that would be surprising, but it's worth writing it down carefully. So what I'm going to do is use the theorem 2.3 to begin with. By theorem 2.3, there exist integers x and y. That was an important theorem, right? You see how much we're using it already. So by that theorem, there exist integers x and y with ax plus by equal to d. That's what theorem 2.3 tells us. The greatest common divisor of A and B can be expressed in this manner. And I'm simply going to divide through by d everywhere. So A over d times x plus b over d times y would therefore be equal to 1. Would therefore be equal to 1. So A over dx plus b over dy would be equal to 1. And now if I imagine this statement right here, where the A is now A over D, and the B is now B over D, right? Then we've basically got this, right? And so by this theorem 2.4, right, A over D and B over D are relatively prime. Just literally by this box. But I'm using the box not with A and B, I'm using it with A over D and B over D. That's the whole proof, very short. So it's just a quick little corollary of the theorem 2.4. One more corollary here. This is corollary 2. And what this one says is that if A divides C and B divides C, lots of results about divisibility here, right? If A and B both divide C with GCD of A and B equal to 1, this is actually a very important corollary. If you have two different numbers that both divide C, and those numbers have no common factors other than 1. When I say no common factors, I just mean that the GCD is 1. 1 is always a common divisor. But if there's no other common divisors larger than 1, in other words, if A and B are relatively prime and they both divide C, then A times B also divides C. You can actually make a larger common divisor, which is the product of A and B. Before I prove this corollary, I just want to make the remark here, and it makes sense that we would consider this. This is not true. Corollary 2 is not true if the GCD of A and B is greater than 1. In other words, if A and B are not relatively prime, then you cannot say this. We could make some very, very easy examples. I'm going to make one that's not the absolute smallest example possible. Maybe if you want, maybe you could pause the video for a moment and see if you could think of an example. Make a number A, make a number B, and make a number C, such that A divides C, B divides C, but A times B does not. It's actually not so hard to make an example. So feel free to pause the video if you want to try it yourself. I think that would be a worthwhile exercise. And then I've got just a little bit of space here. I'll write down the one that I thought of. Okay. So here's the one that I came up with. I basically said, look, 6 divides 24. And 8 also divides 24. Now you can see 6 and 8 are not relatively prime. They have a common factor of 2 in them. Greatest common divisor is going to be 2, in fact. So when you multiply 6 times 8, you get 48. That does not divide 24, of course. This is just my example. Like I said, you guys could come up with your own very easily, I'm quite sure. But when A and B are relatively prime, in other words, when they have a GCD equal to 1, then we can multiply A and B together and still have a divisor of C. Let's prove it. This is not a hard proof. This is just going to involve the basic definitions and the basic results that we've got so far. So I will prove corollary 2 right now. What I'm going to do is I'm going to note that since A divides C and B divides C, I can find a couple of integers. Let's call them R and S. There exist integers R and S with C equal to AR and C is also equal to B times S. So we can just express C in that manner. And since the GCD of A and B is equal to 1, well, then there also exist integers X and Y with AX plus BY equal to 1. That is, again, basically theorem 2.3 again. Okay. Or really it's theorem 2.4, which at least in part is a special case of theorem 2.3. Okay, fantastic. What I'm going to do now, guys, is I'm going to multiply this equation through in such a manner to express C. So C itself is obviously C times AX plus BY. AX plus BY is just equal to 1. So I'm just taking C and I'm multiplying it by 1 right now. And let's re-express that as ACX plus BCY as follows. And I'm going to take the C right here, guys, this C, I'm going to replace it with B times S. So this is going to be A times BSX. And then I'm going to take the second place where I had a C and replace that one with AR. Okay, and the reason I did that, what you might notice now, is that there's actually an A and a B in both terms. And I can factor it out, and that leaves me with SX plus RY. Everything in sight here is just an integer, and we're just doing basic factoring of this whole thing. What was I trying to prove? I'm trying to prove that AB divides C. Isn't that what I have? A multiple of A times B is giving me C. So that does it. AB does indeed divide C. Pretty awesome. Okay. All right, and one last result here, guys, and then I'm just about to the end of this section. One last result here. This one is actually stated as a theorem. It's along the lines of what we've been doing. This one actually goes under the name, though, of Euclid's lemma. We are going to use this result several more times in the future. So this is an important one. Corollary 2 is also important. These are important results here. This one says if A divides BC. So it's kind of reversing the situation of the corollary 2, where we had two divisors multiplied together inside of C. Now we have one number that's dividing a product of two other numbers. But if it's the case that the GCD of A and B is 1, so if A has no common factors with B, then we actually can conclude that A divides C. Okay, so this is a result that's kind of makes sense to talk about it at the same time as we talked about this second corollary here, which I'm going to erase. I want to give myself enough room to prove this theorem, and it's another one of these very short proofs to write down. It's not a long proof at all, so I'll just put it right here. As always, I'm going to start as soon as I know that A and B are relatively prime. I'm going to write AX plus BY equals 1. This is for some integers X and Y. So we write AX plus BY is equal to 1 like that. And then what I'm going to do is kind of like what I had over here. I'm going to multiply. I'm going to get the C involved by just multiplying through by C. So ACX plus BCY is equal to C. So we can certainly write C in that way. But what you'll notice here, see, BC is a multiple of A, right? So since A divides BC, feel free to pause the video if you want to try and do this proof yourself. It's not that bad. We're almost done already, right? So what we're going to do is we're going to find an integer r with BC equal to a times r. And I can then feed that in where I see the BC right here that I underlined. I can change that to AR. So I'm going to have ACX plus ARY equals C. In other words, when I factor out the A, which is kind of the natural thing to do right now, I factor out that A, I therefore conclude that A divides C. So if there's no common factors between A and B, then the entire number A has to actually still divide into C itself. That's basically what that is saying. Okay. Great. A lot of these last few results have been kind of theoretical results about greatest common divisor, relatively prime numbers, and just some divisibility results associated with that. What we haven't really gotten into here in this video is how do we actually find the greatest common divisor of two numbers computationally? How do we actually calculate it? And I've hinted a couple of times that it involves something called the Euclidean algorithm. So in the next video, I am going to talk about the Euclidean algorithm, and we'll certainly do a proof of it and show at least an example of how it can be used to find the greatest common divisor of two numbers, as well as expressing that number as an integer combination of the two original numbers. That'll be coming up in my next video. I hope that this one has been helpful. I hope that you've understood most of what has transpired here. By all means, feel free to jot down questions, reach out to me and ask those questions. And hopefully that will clear up any misunderstandings that you may have up to this point. Thank you guys very much for watching this today. I appreciate it. Take care of yourselves, and I look forward to seeing you again soon. Take care, and bye for now.